Okay, so this will be 23. March 6. We will start with a review of the constructions of the tangent centers. The first one is about the incenter. We'll start with a theorem. The angle bisectors of any triangle are concurrent. Okay, so we defined this point of concurrency as the incenter. Moreover, we showed that this point okay. So because of this, we can introduce the incircle, incenter, and inradius. With this knowledge at hand, we have a different way, maybe a better way to draw an accurate graph. So previous graphs, many of them are sketches. They're not that accurate. To get an accurate graphing, we will start with a circle. If you have a compass, it's easier to draw a circle with a compass. Okay, for any circle. Then I will draw 3 tangent lines, not parallel. Draw 3 tangent lines. As long as they're not parallel. Kind of arbitrary. Then I mark the 3 intersection points. A, B, C. The center. I connect the center with the 3 vertices. Now we can show that these three segments are the angle bisectors of the triangle. Okay, you can see the difference of the drawing we had this time. Previously we started with a triangle. We try to draw the angle bisectors. Then we draw the incircle. So this time we go the other direction. We start with a circle. We draw three tangent lines. Could it be different? Could it be, I could change this a little bit as long as they are tangent. Then we have 3 points. We have a triangle. Then the segment from the vertex to the center, this segment bisect this angle. The segment bisect this angle. A different way. So using this, we also get a formula for the in radius. Okay, who remember this formula? Amy.
Hold on. It's kind of long.
Okay, yes. It's on a big square root
Of the Heron's formula over
Okay.
S, I think.
Okay. So you give a different formula. I've started with yours. It will give is the area over S. Area, we can use the Heron formula. To simplify, we get the final formula. Okay, so it's our first construction about the in radius, in circle, and in center. Our second construction is about the medians. The three medians are also concurrent. So this point of concurrency, we call it the centroid. A property about medians that they divide the triangle into equal areas. Because of this centroid is also called center. More popular name in physics, center of mass. Let's try to draw a graph here. So this one does not involve any circle. Draw 3 median. Spot. The third construction, we consider the perpendicular bisectors. They are concurrent. The perpendicular bisectors of any triangle, they are concurrent. Okay. Moreover, we showed that the point of concurrency it has equal distance to the 3 vertices. Because of this property, we can draw a circle center at O with this distance as the radius. This leads to our definition of circle, circumcenter, circumradius. Okay. Now to draw a picture of this, again we will change the order. Previously we draw the triangle first. Draw the perpendicular bisectors, they intersect at the common point, then we draw the circle. Now we change the order. We will start with the circle. Pick any 3 points on the circle. Any 3 points, your points will be different from mine. I'm going to pick 1, 2, 3, kind of arbitrary. I connect them, I get a triangle. Okay. So the property we have is, okay, let's mark the center. Because the 3 points are on the circle, they have equal distance to the center. Which is the radius of the circle. Okay. So an interesting feature of this is that for any triangle on the circle, it has the same circumcenter. It's the center of this circle. You can move the points around. You can move A to here, you can move B to there, you can move C around. The resulting triangle will have the same center of circumcenter. Okay. Then the fourth construction. We show that the altitude. They are concurrent. Okay. Let each
Wait, can you just go up a little bit?
From here.
Okay.
Okay, Aaron, does the camera work?
No, not right now.
Okay, okay. Zisheng, what about you? Does the camera work?
Not now.
Okay. Fred and Peter? Okay. Now we go to the fourth construction. It's the altitude. The orthocenter. So this word comes from orthogonal. Which means perpendicular. Okay. If you check the homework, you know that for different triangles, the orthocenter may be different. For an acute triangle, we have A, B, C. Acute triangle. We draw the altitudes, perpendicular lines. Draw the altitude. Draw the altitude. For acute triangles, the orthocenter lies in the triangle. But if I have obtuse, then when we draw the altitude, first one easy, but the remaining two, we have to use the extended triangle. We have extended lines. Extend the lines. Then we draw perpendicular. We draw perpendicular. Okay. then the intersection point are on the extension of these altitudes. So let's draw the extension. Let's draw the extension. Then I have to adjust this slightly. Let's mark the perpendicular relation here. But the intersection, the point of concurrency, is on the extended lines. And then we mark this. You can see there's different situations. For an acute triangle, the orthocenter lies inside the triangle. But for an obtuse triangle, the orthocenter lies outside of the triangle. It's very different from the previous three types of centers. If we go to the previous one, the circumcenter always lies in the triangle. Oh, no, I should be more careful. So that is not the case. I have to be more careful for this one. If I choose another pair of points, let's see if I choose these 3 points, let's call this EFG. EFG. Okay, I'll be more careful. Okay, now let's check. For 3 points, EFG on the circle, I draw a triangle. Now I'm going to ask, can you tell me where the circumcenter of this triangle is? Okay. Question. Circumcenter. Okay, who has answer to this? Amy, any guesses?
No.
Kira.
I think it's still the same thing because like all 3 of the points are on the circle.
Okay.
So
Yes.
the circumcenter should still be the center of the circle.
Okay, so the property of the circumcenter is that it has equal distance to the 3 vertices. For this triangle, the distances from the center to all of them equal to the radius. Because of this point will be the circumcenter. Amy, that makes sense? Okay, So now as you can see, our construction, we go to different order. We start with a circle. Then we can pick any 3 points. Initially, I pick these 3. Subsequently, I pick these 3. I pick any 3 points. I get a triangle, and the center serves as the circumcenter of the triangle. You can move the point around. You can draw a different triangle there. Again, this will be the circumcenter. In particular, the circumcenter may be outside of the triangle. This centroid, center of mass, could this point be outside of the triangle? Okay, curious is no. Why?
Because like it's like the medians, so the medians have to like intersect inside the triangle.
Okay, because all the medians are contained in the triangle. Their intersection also contained in the triangle. Okay, so this one we cannot go outside. No matter we have acute or obtuse, we still have the inside. Okay, this one, incenter. Could the incenter lines go outside of the triangle? Okay. According to our definition, this is the intersection of the angle bisectors. So these 3 are all in the triangle. In particular, the incenter is always inside the triangle. Okay, so for the first 2, they're always inside. The second 2, maybe inside, maybe outside. It depends. Now, a boundary case. It's not acute, not obtuse. It's a right triangle. Okay, think about this. How to find the orthocenter of a right triangle. Let me try to draw it. Sure. Do you have guesses for the orthocenter of a right triangle? Where should it be?
Wait, it should be on one of the lines.
Okay, which line? This one, or this one?
I'm not sure.
Okay, so the orthocenter is the intersection of the altitudes. From A to BC, what's the altitude? Kira.
From where?
A to BC.
AC.
AC is altitude. Okay, that's 1. Amy, from B to AC, which one is the altitude?
The B2. Wait, you mean like I don't get the question.
a quick question. How do you draw the altitude from B to AC?
Oh, it's just BC, I
Just
think.
BC because perpendicular. Now we can see these two sides are altitudes. Then the intersection point will be the point of concurrency. Okay, so observation AC and BC are altitudes. Because of this, C must be the orthocenter. In this case, C is also H.
I have a question.
Yes, Aaron.
What about C to AB?
Okay, so this altitude also goes through the point C, right?
Mm-hmm.
So the C is the point of concurrency.
Mm-hmm.
Oh, that's bad. We call this. So as you can see our definition, the orthocenter is the point of concurrency of the altitudes. Now, one altitude, second altitude, third altitude, they both go through the vertex C. So C is the orthocenter. Eric, do you agree? Do you have questions? Because this is the altitude from A to BC. And this is altitude from B to AC. And this is altitude from C to AB. They all go through this point. Okay. So the third one has an important application. So given any triangle, we can draw a circle containing all three vertices. A very important application. The following. For any triangle, there's a unique circle containing all three vertices. Okay. There's a unique circle containing the three vertices. It will be centered at the intersection of the perpendicular bisectors. Okay, so this circle is so for any triangle, there's a circle containing all three vertices. And by our previous construction, it's the circumcircle of the triangle. Okay, we will have 5 minutes break and be back at 8:22. Okay, 5 minutes break.
Okay.
Okay. To find a formula for the circumradius. And I have said before, we will start with the circle.
Isn't it ABC over 4 area?
Yes. Yes. We start with the circle, and I will mark 3 points, kind of arbitrary points. Whatever points you like, you can use your points. So the center will be somewhere near here. Connect. So then we will, so the first step, we will draw a diameter through any of the 3 vertices. I'm going to choose A. You can use different vertices. Draw a diameter. I choose A, so I connect A through the center. I call this point D. So AD is the diameter. Then I connect BD. Then by the inscribed angle theorem, both angle C and the angle D are the inscribed angle for the same chord AB. So these 2 angles are the same. Then because AD is the diameter, and this angle must be 90 degrees. Okay, let's see why. Angle ABD must be 90 degrees. Yes, Amy.
Can I use the restroom?
Yeah, sure.
Thank you.
Okay. Aaron, any guesses why this must be 90 degrees?
Perpendicular bisector.
Perpendicular bisector. So which is perpendicular to which? Which is bisector which?
AB bisects BD.
AB bisects BD. No, they are not. So B is the vertex. AB, if this is AB, then it's bisect. But it's BD is the whole part.
Oh, wait. No, wait, never mind. Hold up.
Uh-huh. Kira.
The bisector of B?
Okay, it's not
What are you
about.
asking? I didn't really-
Okay, let's try to see what's the chord for this angle.
Oh, AG?
AD. Now, what's the center angle for AD? What's AOD angle?
180.
180. By the inscribed angle theorem, this will be half of this angle, right? That's why it's 90. Aaron, do you get this? Because, oops, angle ABD is half of angle AOD. Because AOD is the diameter, this is 180. Okay, that's the proof. Now we are going to apply the trig functions we have learned before. Sine. Okay, Zishan. Aaron. Fred. Who is here? Peter. Okay, Akira, you are you are the only one I'm sure is here. Okay. Sine angle D in this right triangle is a formula for this sine. Kira, do you remember the okay, Aaron, you are back.
Let me guess. AB over AD.
AB over AD. Okay, that's the definition of the sine function. Okay, now I'm going to use the lowercase letters for the side of the three triangles. So AB opposite to C, BC, A, this will be B. Okay. Now we
That's C over 2R, I think.
okay, yes. So the denominator AD is 2R. Let's do a substitution. The numerator AB is our side C. Let's do a substitution. Also, our angle C and angle D are the same. So this is also sine angle C. So we have a new formula. Now if we divide both sides by c, we get 1 over. I leave some space. I want to leave some space. Sine angle c. Make it smaller. It's in the lowercase letter. All right, Aaron and Kira, and I think Amy knows. Have you, do you recall this expression? When did we see this before?
In the law of sines.
What's the law of sine?
Sine angle C over C equals sine angle A over A. And yeah.
Okay, previously we learned the law of sines. All three ratios are the same. Now we know what this ratio is. It's 1 over the diameter of the circumcircle. We know what not only we know they are the same, but we also know what they are. Okay. So this is useful, but it can give us formulas for the radius. So let's take the reciprocal. The reciprocal gives us 2r. Now we use another formula for the area. A, B, sine C. If I draw a perpendicular line from B to is this perpendicular? Let me check. Not that perpendicular. Yeah, this is better. We call this H. So the area is 1/2 B base H. H in this right triangle, H will be A sine C. Therefore, the area equals to 1/2 AB sine C. Okay. We go back to this formula. We have sine C. To have the area, I'm going to multiply AB and I get C times A times B. I put AB as the front. A, B, C. A, B, sine angle C. Okay. Area is half of this. So this will be twice of the area. So the formula R divided both by 2, A, B, C. 4 times the area. Then we use our Heron's formula for the area. We get So this is the formula for the circumradius. Okay. Okay, any question about this procedure? The formula for the circumradius.
Is it gonna be in the homework?
This is in the previous homework. It's the last, number 3, I think.
Wait, if 2r equals ABC over 2 area, then y is R4 area.
So 2R is ABC over twice of the area, right?
Mm-hmm.
We divide both sides by 2. We divide this by 2, multiply the denominator by 2, right?
Okay.
So I get 4 times area.
Oh.
Okay. Okay, so this is about the circles and the triangles. Next, we move on from triangles to trigonometric functions. Circle. Okay. To this purpose, we will recall the two-dimensional coordinate system. Frequently, we will use this x-axis. We draw this, we call it the y-axis. We mark the intersection, we call it the origin. This is x-axis. And this is the origin. Okay. Then for any point on the two-dimensional plane, we draw 2 perpendicular lines, one to each axis. Let's label this as A, this as B. We will call them the x coordinate and the y coordinate. A, the x coordinate. This will be our point P. And B, the y coordinate. Okay, so any point on the plane, we have 2 coordinates, A and B. Sometimes we will use the formula PAB to record the two coordinates, the x coordinate A and the y coordinate B. For example, okay, let's try. I'm going to mark this x, y, O.
Excuse me?
Yes.
Could you also be referring this as HK or something?
That also works. So here I can call this H, I call this K, then I will use HK over here.
Okay. Yeah,
But
sure.
if I call this U and V, I'm going to use U and V here.
Well, that also works.
Yeah, so they are the X coordinate. It doesn't matter what you call it. You want to call anything, maybe M and N also works.
All
They
right.
represent the same thing. Yes. Okay, let's label this. I'm going to mark a few points and ask you what are the coordinates. Draw some lines. Okay, let me give you a few points and ask you for the coordinates. This will be our A. This will be our B, C, D, E, F, G. Okay, a few points here and there. I will give you a few minutes to figure out what are the coordinates for each of the points. A, B, C. Okay, I'll start with Amy. What's the coordinate for A?
1, 2.
And Kira for B.
2, 1.
2, 1. Aaron, C.
3, 0.
3, 0. Zisheng, are you here, Zisheng? Okay,
Yeah.
for D.
-1, -1.
Let's double check. The x coordinate of D is
1.
1 and -1. Okay. It will be okay. 1, -1. Nice. And Fred, Peter, No, okay, Fred, yes. Point E.
D1 and D1.
So it will be -1, -1. Peter, get back to Amy. F.
Oh, E.
Yes, Amy.
-2, 0.
And Kira, G.
-2, 2.
Okay, very nice. An important feature is that these two numbers, if you change them, switch the order, we get a different point. From A, we get to B. So these are the ordered pairs. If the order changes, the point changes. So now I can see P, A, B, and ordered pair. Of numbers. In particular, Q, B, A will be a different point. So all the points on the plane. So two-dimensional, I'm going to use a short term, 2D. Later, we will introduce 3D and higher dimensional objects. So on the two-dimensional plane. The first coordinate, all real numbers. Second coordinate, all real numbers. Will be first coordinate, second coordinate. We use short notation, r squared. So r, all real numbers. Be careful of this square over there. If it's a number, it means square. But if it's a space, this will be the two-dimensional space, not a square. So here means two-dimensional. Okay. Then the two axes, x-axis, y-axis, it divides the plane into 4 parts. So each part, we call it a quadrant. Or quadrant. This will be the first quadrant, second quadrant, third, and the fourth quadrant. Okay. with this, let's back to check. Okay, let's start with Amy. Point A, which quadrant is this point? 1, 2, 3, 4.
1.
First quadrant. And Kira, point B,
First.
first quadrant. And Zishen, point C. Okay, this one a little bit tricky. It's on the axis, so it's not on any of the quadrant. Maybe I will label this first, not applicable. And Aaron, point D,
Fourth.
fourth quadrant. Okay, so these are the wrong numbers. Amy, have you seen this before? 1, 2, 3, 4. Okay, cool. Okay, so the wrong number. And Fred, point E, which quadrant? Okay, back to Amy.
Third.
Third. And Kira, F,
Not applicable.
not applicable because it's on the axis. And Aaron, point G,
Second.
second. Okay, so these are the quadrants. Okay, there's a special object is called the unit circle. Very important object. Unit circle. Okay, so it's the center at the origin with radius 1. Circle. The origin with x coordinate, y coordinate. Okay, let's just draw circle. Move this. Okay, now I label x. No. Okay. Now let's check. Amy, can you give me the coordinate of this point?
It doesn't. Oh. I didn't see the radius one times. 1, 0.
1, 0. Because it's on the x-axis. The radius is 1. So the x coordinate is 1, y coordinate is 0. Kira, what about this one? Okay, Aaron, what's that, Aaron?
Y could also equal 1 and x could also equal 0.
So this will be 0, 1. Okay, also the difference. 1, 0, 0, 1. You can see the order matters here. If you change the order, you go to the different point. Okay, Kira, what about this point?
-1, 0.
And Aaron, this point.
Let's see, 0, -1.
Okay, great. What about this point? What's the x coordinate? What's the y coordinate? In general, it's not easy to give the explicit number for a general point on the circle. So this is why we will introduce the trigonometric functions representation.
Oh, isn't something about x squared plus y squared equals 1 or something like that?
Okay, very good. We don't know what this is for the moment. So let's call this x. We call this y. A formula for this is x squared. A different color. Very important that we will x squared plus y squared equals 1. Okay, why is this? We know the formula. Now I want to check why. Why this give us the unit circle? Okay, think about it. We'll continue from there next time. Any question about this? Let me stop recording.